recording is also started for today's class. So the first thing that we're going to do in today's class is we're going to look at the drift equation and try to understand how it works. This part was not given in the printout of the class note in your booklet, so you need to copy this. Don't start copying right now. For the time, just watch and then you will see eventually. Let's say we have a conductor over here, cylindrical conductor for the sake of simplicity, and we are sending some current through this conductor. Let's say it is carrying I current, and that current is coming out from here. So this is a sectional view of a certain conductor. How much current would be flowing through this conductor? It depends on a lot of factors. Resistance is obviously one, voltage is also another one, but this current is basically the flow of charge. So this current can be attributed or can be expressed in terms of the number of charged particles that exists per volume of this object. Simply what I'm trying to mean is that if you have more electrons passing, you'll have more current. If the charged particles charge is higher, then you're going to have more current passing as well. You don't have the derivation of this equation, so I'm not going to talk much about these variables, not to badger your mind about this. Let me just write the equation straight away and we'll take it from there. The drift equation, the equation is called drift equation, or sometimes also called electron. No, drift equation is good. Drift equation, this is the name. I equals to N A V Q. এটা কপিতে লেখো, লেখার পরে এই পার্টসগুলোকে আমি এই পার্টসগুলো ডিক্টেট করতেছি, এই পার্টসগুলোর ডেসক্রিপশন এভাবে লিখবা। আচ্ছা, কিউতে লেখো, বললাম শোনা যাচ্ছে? কিউতে লেখো চার্জ অফ দ্য চার্জ ক্যারিয়ার। ব্র্যাকেটে লিখবা ক্যাপিটাল সি রিপ্রেজেন্টস দ্য ইউনিট চার্জ অফ দ্য চার্জ ক্যারিয়ার। ইউনিটটা হচ্ছে কুলম্ব। ভিতে লিখো, কমাতে লিখতে পারো, তাহলে ইজিয়ার হবে, স্পিড অফ দ্য চার্জ ক্যারিয়ার। ব্র্যাকেটে লিখবা মিটার পার সেকেন্ড। এতে লিখো cross sectional area of the conductor. Cross sectional area of the conductor. ব্র্যাকেটে লিখবা মিটার স্কয়ার। এনে লিখো number of charge carrier per volume in the conductor. Number of charge carrier per volume in the conductor. লিখছো? Number of charge carrier per volume in the conductor. ব্র্যাকেটে লিখবা meter to the power -3. This is a number per volume. So how many in unit volume? So উপরে হচ্ছে জাস্ট একটা নাম্বার আর নিচে হচ্ছে মিটার কিউব। ওই জন্য এটার ইউনিট হচ্ছে শুধুমাত্র this one only has a unit of meter cube, meter to the power -3. Now the reason I asked you to write out all of these units is just to give you a bit of idea of homogeneity of this equation, because we are not showing you the derivation. If we just multiply all of these variables, we should be able to get ampere. So let's try to do that. Coulomb multiplied by meter per second.
Derivation লেখা আছে, derive and use.
এটা কোথায় আছে?
Syllabus.
Derivation আছে
sir.
মানে লেখা আছে like derive and use for the kind of current carrying conductor, the expression I equals to A and B cube.
হ্যাঁ, কি বলো? তাহলে ওটা তোমাদের দেখা যাবে, বাট আমি যতটুকু জানি আপ টিল লাস্ট অফ মাই নলেজ এটা 1 মিনিট দাঁড়া, আমি দেখে দিচ্ছি, 1 মিনিট দেখে নিচ্ছি। বাট থ্যাঙ্কস ফর দ্য আপডেট, thanks for the update. If it's in the syllabus, then I'm more than happy to teach you. কই জানি গেল সিলেবাস তোমার পরীক্ষা 2021 এ। হ্যাঁ, একটু পর খুলো খুললো, শব্দ কোনো সমস্যা হবে না, it's perfectly all right. Derive and use for a current carrying on to the expression of I equals to NAVQ, where n is the number of density of charge carriers. Okay, okay, no problem. Uh, I'm looking up your book because I don't have a solid copy of the book, just to find out that how much derivation information did they provide for you to know. Just a second. This should be available in this one, I believe. Slow flow, fast flow. Yeah. Okay, so this is the derivation that we have. So we can actually pretty much start from this point. No big deal. Okay, you already wrote the idea, so let me just zoom in on it, and we're taking it from here. So this is the equation that we have. The reason v is basically called the drift velocity. Did you write drift velocity, or what did I say? Speed of the charge carrier, right?
Yes, sir.
ওটার পাশে বা নিচে একটু লেখো স্ল্যাশ দিয়ে লেখো drift velocity. This is the term that you need to be acquainted with. Drift velocity. Or you can actually write mean drift velocity as well, because for an MCQ this might be a keyword, mean drift velocity. I'll tell you why this is called mean drift velocity. Why not only drift velocity? I'll tell you that. Here's the thing. Let me go ahead to elaborate this part. The reason we are calling this Q the charge of the charge carrier, because current does not essentially and only flow through the conductor. Current also flows through electrolytic solution as well. Whenever you have electrolytic solution, you can have charges which have more than the charge of a single electron. For example, if you have a copper ion Cu2 plus, if you have an iron ion, if you have Fe3 plus, if you have a zinc 2 plus, sodium single value. So in those cases we also have current flow, and those things can give you a charge value that is higher, or a fixed multiple, integer multiple of the charge of the electron in terms of magnitude. That's why for the generalized purpose of this description, we use this equation I equals to NAVQ, where the Q represents the charge of the charge carrier, which could be an electron or which could be a ion depending upon the scenario that you are handling. However, if we only consider the equation for metals always carry charge by exclusively electrons, then we can essentially replace the Q by E, because that simply makes sense, because metals only have electrons. The reason we call this term mean drift velocity is this thing. You have to understand one thing. The way metallic bond works is that if you have a piece of metal, you have a lot of delocalized electrons, and all of those delocalized electrons practically come up to the surface, and 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 underneath this thin layer of electrons, the layer is pretty thin because electrons are very small, and but they are in the same number. If this is an uncharged metal piece, then the electron number and the proton number within the block is same. So the core is positively charged core because they have lost electrons. I'm giving only 1 plus here, assuming this is a sodium piece or group 1 element. And the on the outer side, it is coated with the free electrons. Now these free electrons are not essentially stuck in one place, pretty much like Brownian motion that you've come across. It's not Brownian motion, but pretty much like Brownian motion, that even though you are not supplying any heat to a system, because of Brownian motion, liquid particles or gas particles, I mean fluid particles, will have random motion. We know this. So similarly, electrons will also move around randomly from one place to another place, just because of no reason. whenever we'll apply a voltage across this conductor, let's say we apply a plus positive voltage over here and a negative voltage over here, this will cause these electrons to have an overall flow to the left. So electrons are going to flow this way because this is the electron enriched section and this is the electron deficiency section. So to rebalance the whole imbalance, they are going to start flowing, or we say the conventional current is going to flow this way. Now what do I need you to understand, that it's pretty much like uh, I mean, whenever electrons are going to actually go in this way, all the electrons are not going to flow in a perfect straight line. Some electrons are going to go this way, some electrons are going to this way, and because of random movement, it is also possible some electrons can also have a little bit of reverse movement as well. But the overall flow of this whole thing will be what? From right to left, from the negative end to the positive end. Because all the individual electrons will not have the identical velocity, they can have different velocity values. That's why we prefer to use the term mean. That's why we call it mean drift velocity, which is the average. এই কনসেপ্টটা বুঝা গেছে কিনা, that individual electrons can have different velocities, but whenever the voltage is applied, there is an overall single direction that we can consider.
স্যার
জি,
ওই পার্টটা কি আরেকবার বলবেন কিভাবে মেটালটা চার্জড হয়?
কোন পার্টটা?
স্যার ওই যে মেটালটা চার্জড হলে কি হয় ওই পার্টটা আরেকবার বলবেন?
Oh, this is basically the description of the metallic bond. The way metallic bond works is that every single metal atom uh, gives up their outer shell electron. If it's sodium, is they're gonna give up the one electron. If it's calcium, two. If it's aluminum, three. So on and so forth. These electrons do not, at that point when the atom releases those electrons, they become positively charged, and the electrons become delocalized electron. Delocalized electron means that they are not owned or possessed by any singular atom in the metal piece. Rather, they become a overall property, combined property, or let's say own property of the whole metal piece. So all the free electrons, because they repel each other, that's why they come to the surface and try to maintain maximum average distance between them. That's why they always come to the surface. However, the core remains positively charged. So because the core is positively charged, the core keeps on attracting that layer of the or layer of the electrons. So the reason metals can be very strong is that there is a continuous attraction of on the outer coating of the electrons from the inside. There is a positively charged ions. The more electrons and the more charge you have, the more stronger is the attraction. That's why aluminum, although quite light, can be very strong, because aluminum releases 3 electrons per piece, whereas sodium can be like butter, because sodium only releases 1 electron in its shell, so the attraction is not that small. I mean, this is very much simple. This is very much similar to, like, if you have a, let's say, if you have if I give a simple example, let's say ঝাড়ু দেওয়ার ঝাঁটা আছে না, লাইক বিছনা ঝাড়ু দেওয়ার ঝাঁটা, নারকেলের শলা, দেখছো তো সবাই? হ্যাঁ, let's say you have one of those things, and whenever it is in its normal form, you can very easily bend the whole thing. I mean, you can bundle it in your hands, in your within your grip, and you can bend it. But let's say if I take a strong piece of rope and wrap around those jhatashala really tightly and tie it up together, this whole thing would become much too stronger than before. It would be very difficult to bend and something like that. So that squeezing effect actually strengthens the material. That's exactly how metals get their strength.
আচ্ছা স্যার, স্যার যখন আনচার্জ থাকে তখন তো ইলেকট্রনস গুলো রিলিজ হয়ে যায়,
যখন
আনচার্জ থাকে তখন তো
this is the case. I mean, whenever we do not apply any potential, or it is not induced to have any charge, then there will be equal number of protons within the positive core, and also the electrons on the outer shell. So there will be equal number. But whenever we'll start to flow current through it, in that case, I mean, let's say there is a conductor within a circuit. Okay, so let's say this is a resistor, there is a battery over here, this is conducting. So let's say conventional current is flowing this way, electrons are flowing this way. If at any point of time, if it is asked, while the current is flowing, is this thing charged? The answer is no. This object is not charged, because the number of electrons which is going to enter from right to left is the same number of electrons which is going to leave from left to right. Sorry, right to left over here. So electrons are flowing through, but there is not an overall difference between the proton number and the electron number. Electrons are continuously substituting. Something like what you know about the equilibrium point for a bidirectional reaction. এটা জানি কি বলে? What do you call those reactions which happens in both directions?
Reversible
reversible
reaction.
reaction.
Reversible reaction, exactly. So something like that, the equilibrium point of a reversible reaction. Or for example, let's say if there is a country where you don't have any population growth over the last 10 years, that doesn't mean everyone has become immortal. That means that the number of people dying is equal to the number of people growing, taking birth, something like that. So this is not charged, but there is equal number of electrons at any instant for the uncharged condition, so the attraction always remains the same. Hence, even though it's carrying electrons, the metal doesn't become flaccid or doesn't become weak. It still can keep its strength.
Okay, sir. Thank you.
No problem. So এটা এখন আমরা জিনিসটা দেখবো সেটা হচ্ছে how can we go ahead to derive this equation. The deriving is given over here, so I'm going to show you, explain the derivation of it. This is pretty well written. Look at the wire shown in figure 9.9. Its length is L. We imagine that all the electrons shown travel at the same speed v along the wire. Now imagine that you are timing the electrons to determine their speed. Timing means you are observing them and measuring their distance over time. You start timing with when the first electron emerges from the right hand of the wire. You stop timing when the last of the electron uh, uh, you stop timing when the last of the electrons shown in the diagram emerges. So they are showing this figure. So we are trying to calculate how much, I mean, all if all the electrons are going out of this thing, I mean, from left to right, if all the electrons are going out, then we can calculate exactly how many currents are flowing, and we can divide that by the amount of time that it takes for all the electrons to go out, and that total charge transferred over that time can give you the value of the current. So that's what we're trying to do. In the time t, all of the electrons in the length L of the wire have emerged from the wire. We can calculate how many electrons this is, and hence the charge that has flowed in time t. So now we are trying to first calculate the number of electrons. Number of electrons will be given by number density into volume of wire. So the n is a variable that was defined as, the way I wrote you is that number of charge carrier per volume, or over here in your syllabus they have also used the term number density. Well, per volume can very well mean density. So this is given over here. This means how much would be available in unit volume. So if you multiply this number by the volume of the wire, you can very easily find out what was the total number of electrons present within that wire. So A is the cross-sectional area of this conductor, and L is the length of this conductor. So if you multiply n into A into L, here the Al gives you the volume, you get the total number of electrons. Then if you want to calculate the total charge of the electrons, simply multiply this number of electrons by the charge of an electron, so you get NaLe. This is the total amount of electrons charge that can be available within this free electrons charge that can be available within this length of this material. Now we can find out what is the current, because we have calculated the total charge that was available, and if it takes t time for this electron to travel all the way out, it means this very last electron ultimately reaches over in the very right surface, and it takes t time to reach up to the surface, then that is the amount of time for which this amount of charge is going to go out from this conductor. What I want you to understand that when these electrons are going to go out of this right side, the left side will not become empty. This will be continuously refilled by the electrons incoming from here. We are trying to see a section of the electrons as a unit. So something like that. So we have the current over here, which is basically the total amount of charge over the time, and then we are substituting the basic equation for speed. Speed is given over speed over time. So here L divided by T, this L divided by D, this fraction is replaced by V. Ultimately you get I equals to NAV. That's basically the equation. The key part is to understand how to get the charge amount. So this is the part that you need to understand, and the rest of the part is actually pretty basic. The moving charge carriers that make up a current are not always electrons. They might, for example, be ions, positive or negative, which are charged as Q as multiple V. Hence, we can write the more general version of the equation as I equals to NAVQ. Work example 3 shows how to use the equation and calculate a typical value of V. So we have an example over here. They have given us all the variables, so we can calculate the V value over here. Now, this is the part that which shows over here as slow flow is really important for you. You have some significant MCQs come from this thing, including graphs as well. So let me discuss this part. It may surprise you to find that, as suggested by the result of work example 3, electrons in a copper wire drift at a fraction of a millimeter per second. So you can see over here, calculate the mean drift velocity that the electrons in a copper wire of a cross-sectional area of this much meter square carrying a current of 1.0 ampere. So if we have this situation of 1.0 ampere current flowing through a copper wire, what should be the drift velocity of this situation? The question says the electron number density for copper is 8.5 × 10⁸ per meter cube. If we rearrange the equation, we can replace all these values over here. The speed is given by this number. You can see this is, so you can see that the electrons are practically not moving. They are like they're slower than snails. They are just creeping, not even moving. They are creeping through this thing, but that creeping can give you 1 ampere current. If you wonder why, because copper has a really large number of electron volume per meter cube. There are this many free electrons available, so they a lot of the electrons are moving, and they're moving pretty slowly. So overall, you can have a pretty good amount of charge flow. So that's that. And then it says that this is here is a part. Uh, to understand this result fully, we need to closely examine how electrons behave in a metal. The conduction electrons are free to move around the metal. When the wire is connected to a battery or an external power supply, each electron within the metal experiences an electrical force that causes it to move towards the positive end of the battery. The electrons randomly collide with the fixed, uh, but vibrating metal ions. Okay, yeah, the core. Their journey along the metal is very haphazard. The actual velocity of an electron between collisions within the actual velocity of an electron between collision is of the order of magnitude of 10 to the power 5 meter per second. So what this they are saying that, let's say an electron is making its journey through the metal ion, and the, let me just draw a zoomed view of this part. Let's say I'm gonna zoom in on this one by a really large scale. Don't have a idea for the scale. Let's say this is the vibrated. This is the actual zoomed in view for the positive ion. So we have all the positive ions over here. So they're making a rough surface. Not only they are making a rough surface, they are also vibrating. They are vibrating in random directions. And on top of this, positive layers, we have all the small tiny electrons trying to make their journey from right to left. So this is basically like a bumpy road, where the road is not essentially curvy, it is also jumping on it up and down. So the electrons cannot actually flow in with peace. They will definitely have collisions. But they're saying that if an electron hits one of these positive ions, between that speed to the next hit to another positive ion, that in between speed of the movement of electron can be within the order of 10 to the power 5. That's a really fast movement. But since this movement is haphazard, I mean, you cannot essentially control that which electron is going to hit which fixed ion, and this is actually basically very random. That's why the average velocity or mean velocity can prove to be this much small. So this is the scenario. The journey along the metal is very haphazard. The actual velocity of an electron is this much, but its haphazard journey causes it to have a drift velocity towards the positive end of the battery. Since there are billions of electrons, we use the term mean drift velocity via the. So they basically explain what I just told you a bit earlier. So which is a good this is a good description. It makes good sense. Figure 9.10 shows how the mean drift velocity of electrons varies in different situations. We can understand this equation, this using the equation IV equals to I divided by NA. If the current increases, the drift velocity V must increase, that is V proportional to I. Okay, using this equation is pretty simple. You know how the proportionality equations work. Uh, Here, whenever we are writing V proportional to I, we have to assume that all of these other three variables are remaining constant. So if you are so if n is a constant, which means if you are constant, n is a constant, this means what? For an experiment, n is kept constant. It means you are going to do experiments with different specimen, all of which should be made from the same material, so that n is not a variable for all of your individual readings. That's what means that n is a constant. Cross-sectional area constant means all of the wires would have the same diameter, or if it's the same cross-sectional area. And E is a basic constant for metals, so E doesn't bother us. So in this case, V is proportional to I, which means if drift velocity increases, current will increase. And similarly, if the wire is thinner, the electrons move more quickly for a given current, which means if you have two wires connected over here, here they have shown a good example. Let's say, have a look. Uh, where was the original figure? So the original figure was this one.
স্যার
Yeah, here.
স্যার আমার এখন একটা ক্লাস আছে, আমি একটু লিভ নেই।
Sure, no problem. পরে
Okay.
পরে একটু ইউটিউব থেকে দেখে নিও, ঠিক আছে?
ওকে স্যার।
Okay, all the best. So let's say this is the primary figure where I current was flowing and I current was happening for a drift velocity of V, only V. If we somehow double the current, if you wonder double the current can be very easily achieved by doubling the voltage. Let's say the voltage was double, so double current is flowing over here. It is the same conductor, it is the same cross-sectional area. So in this case, double current must be executed by double speed. So double current, double speed. If we have this kind of a situation where we have a thick part over here, we have a thin part over here, and once again, if we have only I current flowing through here, if I current flowing through here causes this cross-sectional area of electrons to have a speed of drift velocity of V, mean drift velocity of V, when the cross sectional becomes half, the speed has to become double, because you now have less number of electrons available through this part of the conductor compared to the number of electrons available over here. So this is very much like a valve. I mean, do you guys know how a valve work? Not valve. This is very much like a venturi. Actually, you don't know what a venturi is. Let me just tell you this thing. Whenever we open the hand shower of a washroom, what happens? Water squeezes out really fast, right? Why does the water squeeze out really fast? This is because inside the pipe the water is flowing through a large tube, but when the faucet, when the hand shower is open, all of those very tiny holes have pushes out the water at a very high speed. So if you want to keep the flow rate has to be same. The amount of water volume per second or kg per second water that flows to the hand shower tube is the same. It has to be the same of the amount of water that flows out of this pipe, or all of these uh, small pipes. So to achieve this, the in the small cross sectional parts, the in the small cross-sectional parts, the particles have to move really fast to make up for the small lack of presence of particles. So do you have the same number of particles? For example, over here you might have, let's say, 10 particles moving at 1 meter per second. You can have over here 2 particles, 20 particles moving at, 20 particles now. You can have 5 particles moving at 4 meter per second, giving you the similar effect so that you have a equal flow rate. So that's the idea, that if we have to apply V proportional to 1 by A, you have to understand that this has to be applicable when all the other things, I, N, and E, they are constant. And last thing, if we have if we want to compare between multiple different conductors where N is to be considered as a variable, which means you're going to have same dimension and same current flowing through multiple conductors. Now there is a catch. If we want to achieve this experiment, we have to precisely maintain an ammeter with a variable resistor with the source, because you want to keep the current constant. If you use different conductor for any of these experiments, to be honest, this is true. If you want to use different conductors, naturally their resistance would be different. Do you understand this part? Different conductors, either made from different material or have different dimensions, they are bound to have different resistors. Am I correct?
Yes, sir.
So if you have different resistors of different conductors, either because of different dimensions or because of the choice of material, this is always true that if you want to keep equal current, you have to change the voltage. For this experiment, the voltage is not a part of our equation. We are dealing with the current. So you have to have a large enough voltage supply, and you have to have a variable resistor connected in series with that conductor. And obviously you're going to have an ammeter. What you're going to do, you're going to close the circuit, operate your variable resistors to make sure that the current is the value that you are doing all of your experiment with. If you want to keep your current constant, every single time you change your metal piece with a new one, you have to readjust the variable resistor value to get the exact same value of current if you want trying to keep the current constant. So that's pretty important, that if for the apparatus setup, we would require a variable resistor with a source and also an ammeter, so that we can observe what is happening and we can control what is happening. The reason I'm telling you this experimental part, because sometimes they will give you this thing, and this idea might not be very much useful for you for S level, but this would be very useful for your S level lab. It should be, or also in the paper 5, which comes in your A2 planning and habi jabi. So this is the part that is about this whole thing. We can also have
Sir.
it over here. If we have here, you can see V is proportional to 1 by N, which means if you have a large number of charge carrier, they can move pretty slowly, or if you have a small number of charge carriers, they will have to move really fast. So if you compare between two identical piece of conductor, let's say one made from aluminum, the other one made from let's say sodium, obviously in sodium there would be fewer free electrons, because sodium has a valence sodium only gives a 1 electrons in its lattice. So if you apply if you maintain equal current through both of these pieces, which are dimensionally exactly identical, obviously the drift velocity should be large in which one, sodium or aluminum? Which one should have a larger drift velocity?
Sodium.
Sodium should have a larger drift velocity. Beautiful, because should have a much bigger n value compared to sodium. So aluminum would work with a bigger number of electrons, so it will move slowly. You can see over here V proportional to 1 by N. Bigger the number of free electrons, smaller can be the speed, and vice versa. Yes, Zara bolo. I was in the discussion. Bolo, you have a question?
স্যার ওই যে এখন একটা সাইড থিনার আর একটা সাইড থিকার পাইপটা আছে না,
হুম।
ওইখানে আপনি বললেন না ইলেকট্রনস গুলো ওই যে কয়েকটা স্পিডের ভ্যালু দিয়ে একটু কম্পেয়ার করলেন না, ওই পার্টটা কি আরেকবার বলবেন?
শিওর, দেখাচ্ছি, আমি করে দেখাচ্ছি, তাহলে তোমার বুঝতে সুবিধা হবে। মনে করো হচ্ছে I equals to NAVE. Now we need to compare these two variables. So let me just subject V, I divide by N AE. And মনে করো, let's say we are going to compare multiple different conductors where the cross-sectional area is different. So one is thin, one is thick. Length doesn't matter because length is not involved here, so we don't have to bother about length. But what you have to make sure that all of them are having the same amount of current. That's where the rheostat and the ammeter comes in. So try to understand that for this proportionality to work, V proportional to 1 upon A, the product of these three things has to be a constant, right?
Yes, sir.
And মনে করো, the product of these three things, let's say this ratio for our experiment, I'm just giving as you know, let's say this value is 100. তার মানে হচ্ছে no matter what value of V and A we choose, the product of V into A, this product should always be 100 as well, because that's what you can see over here. If you just do the cross multiplication, VA equals to a constant, I'm going to write K, which is equals to, let's say, 100. So if you double the cross-sectional area, V should become half. So so let's say in a certain scenario you have a cross-sectional area of 20. In that case, the speed will be 5. If you have a cross-sectional area of 10, your speed will be 10. If you have a cross-sectional area of 50, your speed can be 2. So that's what I'm saying.
আচ্ছা স্যার। আর স্যার ওখানে যে বইয়ে এই সেম পাইপটার মধ্যে 2V লেখা না, তো যেখানে 2V ওখানে 2I ও হবে না?
No. These two parts of the conductors are connected in series. How can you have different current?
আচ্ছা স্যার, বুঝেছি।
Current has to be same because they're connected in series. It's the same current, but here the cross-sectional area is half. So if this is A, this cross-sectional area is A by 2. That's the key difference. বুঝা গেছে কি so far?
Yes, sir.
আচ্ছা, বিউটিফুল। আচ্ছা, এরপর আর ডিপ ভেলোসিটি নিয়ে কিছু নাই। কি বলে যে নাম তো ভুলে যাই কেন। ইফা, থ্যাংক ইউ ভেরি মাচ ফর নোটিফাইং দ্যাট আই অ্যাকচুয়ালি ডিড নট নো দ্যাট তোমাদের সিলেবাসে এটা ডিরাইভেশন দিছে। আগে মনে হয় ছিল না, অর নোটসে নাই দেখে আমি ভুলে গেছি, তাও হইতে পারে। বাট রিয়েলি থ্যাঙ্কস ফর দ্য হেডস আপ। বুঝা গেছে কি এ পর্যন্ত সবার? কার কোনো কোশ্চেন? এনিওয়ান?
Sir, I had one more question.
Sure, go ahead.
আচ্ছা স্যার, সেমিকন যদি ড্রিফট ভেলোসিটি বাড়ে তাহলে কি কারেন্ট বাড়ে না?
Well, if all the variables are constant and only drift velocity increases, then obviously current will increase, because the equation, see, you can see the equation over here. If you take n a constant, I can write I proportional to V. So if V goes up, I also goes up by the same proportion. Yes.
তাহলে স্যার সেমিকন্ডাক্টরসদের বেশি ড্রিফট ভেলোসিটি থাকে কেন কন্ডাক্টরসদের থেকে?
এটার কারণ হচ্ছে সেমিকন্ডাক্টরসদের তো বেসিক এন এর ভ্যালুই হচ্ছে অনেক কম। একটা মনে করা হচ্ছে, let's say you have a 1 centimeter cube piece of copper and you have a 1 centimeter cube piece of silicon. The number of free electrons available within the copper cube is orders of magnitudes, tens of orders of magnitudes higher compared to the number of free electrons available or conducting electrons available within the silicon piece. So if you connect them into series and apply a voltage across them, same current has to flow through both of them. So if I same for both of the pieces or both of the conductors or both of the they are not conductor, but let's use the term conductor over here. If I same for both of this material, if I same for both of them, then the one that has a higher N can essentially work with a lower V, and vice versa. So copper will has a large N, so it can work with a small V, whereas silicon piece doesn't have that many n, so it has to work with a higher v. That's the reason. And this is also the case why, I mean, from this equation you to understand that why the semiconductors have a low resistance with higher temperature. When temperature goes up, more valence electrons from a semiconductor's outer shell can reach to the conduction band. So with the increase of temperature, a semiconductor piece experiences a significant increase in its n value. As n goes up, I also goes up, which essentially means R has gone down.
বুঝেছি স্যার, থ্যাংক ইউ।
No problem. এই পর্যন্ত বুঝা গেছে কি সবার, মানে ক্লিয়ার হয়েছে কিনা, কার কোনো কোশ্চেন? Acha. So that is the discussion for the differential equation. We're gonna see problems about that as well. No big deal. We have some time left, so I'm gonna get back to the MCQ solution that we started our today's class with. No. বলো এখান থেকে যে কোশ্চেনগুলো অ্যাটেম্প করছো কোনটা কোনটা পারো নাই, কোনটা কোনটা পারছো আমাকে বলো, I'll help you for those. এটা আসলে ফুল ম্যাক্স চেঞ্জ করা থাকলে ঝামেলা হয়। বলো মান, আমি একটু 3 মিনিটের মধ্যে আসতেছি, আমার একটু পিচ্ছি ম্যানেজ করা লাগবে।
ওকে স্যার।
সো এখানে আমাদের প্রথম প্রবলেমটা কি ছিল? 10.2 তে যাব। দাঁড়াও, 5
2 ছিল স্যার।
আচ্ছা, 2 তো পারার কথা, 2 পারছো?
ইয়েস স্যার।
আচ্ছা বলে যাও এই পেজ থেকে কোনটা কোনটা পারো না সেটা বলো, আমি সেগুলো দেখাই। আচ্ছা 5 টা একটু আমি আলাপ করতেছি। 5 এর the basic idea for the 5 is that a researcher has 2 pipes of copper of the same volume. All of the first piece is made into a cylindrical resistor P of length X. All of the second pipe is made into uniform wires, each of the same length X, which he connects between the two parts of a negligible resistance to form a resistor Q. How do the electrical resistance of P and Q compare? So this is the part that I want you to understand. A researcher has 2 pieces of copper of the same volume. So he has 2 pieces of like this. He connected one directly with a source and trying to flow some current, and then he divided the second piece into 1 2 3 4 5 6 7 wires and then connected them into parallel. So what I want you to visualize for this problem to understand, let's say this is the first wire. Let's say this is the first wire, cylinder, and then rectangle. What he actually did, or what I want to observe, that he cut off this wire lengthwise into 7 pieces. So let's say 1 2 1 2 3 4 5 6 7. My drawing is not equal, but you have to understand that all of these sections have equal cross-sectional area. So he cut this thing into 7 equal pieces and connected them into parallel. So you just separate them out lengthwise. So you have to understand, in that combination that we have, where we have 7 different wires, each of the wire has, let's say the total resistance of this whole cylinder is R. Assume this thing. Each of these wire has a cross-sectional area of 1/7. If this one has an area of total area of A, this wire has an area of A by 7, which means one of these wire will have a resistance of 7R. You have 7 R's connected in parallel. So what should be the total resistance? 7R by 7. So your common resistance of this whole thing is still R. That's basically it. That the same thing has been split into multiple pieces and connected in parallel. So basically it's the same piece, just currents are flowing in different cross-sectional area which are separated out. That's why the correct response for this question should be which one?
C স্যার।
C is the correct response. Yes. বুঝা গেছে কিনা?
ইয়েস স্যার।
আচ্ছা এই পেজ থেকে আর কোনটা সমস্যা না, বাকিগুলো পারছো? এনিওয়ান রেসপন্ড করো তাড়াতাড়ি। পারছো এই পেজ থেকে? কি কি পারো নাই?
স্যার 9 কি ডি হবে?
আনসার কি দেখো, আনসার কি বের করি। Where is my answers? Okay. 10.2 এর 9 এর আনসার হচ্ছে ডি। নাইন দেখি, সমস্যা নাই। নাইন বলছে হচ্ছে in which arrangement of the resistors the emitter has resistors in each arrangement of this resistor the emitter has a resistance of 2 ohm. Which arrangement gives the largest reading on the emitter when the same potential difference is applied between the points P and Q? So we are basically trying to figure out which of these combination will have the least resistance so that you can have highest current. So add up here. The total resistance of this combination is 1 plus 2 plus 2, 5 ohm. Let me copy this. The total resistance of the first combination is 5 ohm. Here it should be 1 and 2 parallel plus 2. 1 and 2 parallel gives you 0.67. And this is 2. So the total common resistance is 2.67 ohm. Here you have 1 and এটাকে ভুল বলছি, আমার ক্যালকুলেটর করেছে আমি জানি না ভাষা বদলানোর পর, একটু ক্যালকুলেট করে দেখো তো কত আছে এটা। 1 inverse plus 2 inverse whole inverse, ঠিক আছে না এটা?
ঠিকই বলেছেন।
আচ্ছা, here we'll have 1 ohm and here we'll have 2 ohms, so 1 plus 2 will give you 3 ohms and 2 ohms in parallel, so 3 inverse plus 2 inverse whole inverse কত হয়? 6/5. এরকম না? না,
Yes, sir. 1.2.
মানে 1.16 66 এরকম।
1.2 আসে।
আচ্ছা এক্স্যাক্টলি 1.2 আসছে। আচ্ছা 1.2 ohm, এই কম্বিনেশন টোটাল রেজিস্ট্যান্স কত হবে? 1 ohm 2 ohm 2 ohm all in parallel, so 1 inverse plus 2 inverse plus 2 inverse কত হয়?
Half.
So since this one has the smallest resistance, obviously this one will have the highest current, but this is not correct. I just calculated the common resistance of all the branches, which was done mistakenly. Actually, up till now this we are good. এটার common resistance actually দরকার ছিল না, আমি এটা ভুলে হুজুগে করে ফেলছি। সেটা হচ্ছে whenever we connect the same voltage across this point, this emitter will read the branch current for this one. এই ব্রাঞ্চে কারেন্ট কত দেখো তো, এই ব্রাঞ্চের রেজিস্ট্যান্স কত? এই ব্রাঞ্চের রেজিস্ট্যান্স হচ্ছে exclusively 3 ohm. That's what we are trying to find out, because we are trying to compare the current between the reading of the ammeter, not the total current that flows through the whole combination. We are trying to compare the reading of the ammeter. So the ammeter branch over here carries has a resistance of 3 ohm altogether. So that is the relevant resistance. And in this case, the ammeter branch has a resistance of only 2 ohm. এখন তুমি কম্পেয়ার করে দেখো যে কোন কেসে তোমার লিস্ট রেজিস্ট্যান্স আছে, যাতে করে তুমি হাইয়েস্ট কারেন্ট পাবা। আগে ক্যালকুলেশন দুটো দরকার ছিল না, ওটা ভুলে করে ফেলছিলাম, মাই ব্যাড।
স্যার বি এর ক্যালকুলেশনটা কেমনে করলেন আরেকবার বলবেন প্লিজ?
These two are in parallel. 1 inverse plus 2 inverse whole inverse. This is the common resistance of the parallel combination plus 2.
আচ্ছা স্যার, আমি এগুলো ভুলে গিয়েছিলাম তো তাই সরি স্যার।
তারপর এই পেজে আর কোন সমস্যা? 10 পারছো? 10 is actually quite simple. Simply 10 এ যে কাজটা করা লাগবে সেটা হচ্ছে we are trying to find out that what should be the fraction of current that flows through here. এটা বের করা খুবই সিম্পল। প্রথমে আমরা যে কাজটা করব, the first thing that we're going to do for this question, we're going to find out what is the voltage across these two connection points. To find out the voltage, we have access to the full current, we have access to the calculation of the full resistance. So you will calculate the common resistance of this thing, that is 1 inverse plus 2 inverse plus 5 inverse, whatever you get, multiply that by the full current. So full resistance into full current gives you the full voltage. So you get the voltage across these 2 points, and then use that voltage and only this branch resistance to find out the emitter current flowing through this branch. That's pretty much it. এটা কত আসছে answer? Ouch.
So C হবে answer.
আচ্ছা, ক্যালকুলেশন ঠিক থাকলে আনসার মিলে যাবে, ঝামেলা হওয়ার কথা না। এখানে মনে হয় আর কিছু ছিল না। Let's have a look for the other question. 17 was another question that I asked you to attempt. I'll take this out. 17 কি পারছো সবাই? মানে মিলছে কিনা? এটা কম্পেয়ার করে অ্যাকচুয়ালি খুব সহজ। আমি সহজ বুদ্ধিটা বলে দিচ্ছি। Whenever you have this kind of problems, you can always do assign values if you are more comfortable with calculation. Assign values means if you assign a voltage in this source, and then you can very easily calculate all of the individual voltage values and the current values as well, and that will lead to your answer, and you can compare those numbers very easily and choose it over here. So that is one of the easiest way to go for it. So let's say you assign, let's say 10 volt, 9 volt, 5 volt, 6 volt, doesn't matter. Calculate the total current and then calculate the separation of the voltages and slowly go ahead from there. That's one way to do it. The other way to do it, that the way I personally prefer to do this, is can look like this. Is by idea or fractional idea. Have a look. The common resistance of this whole thing would be, I think, 2 ohm. 3 inverse plus 6 inverse whole inverse করলে কত হয় দেখো তো? 2 হয় না?
Yes, sir.
Yes, sir.
So the common resistance of this parallel combination is 2 ohm. The common resistance of this parallel combination would be 1 ohm. So I'm going to do the calculation for this. I'm not going to do the calculation for this because I can see 2 and 2 in parallel. So 2 divided by 2 gives you 1 ohm. So if you just have a good observation, that you would see that this circuit is primarily a series circuit. We have this part as a series component, and we have this part as a series component. Within this series component, there is a parallel combination, but they're actually in a series. So within the series combination, the voltage gets shared in terms of their ratio. So this source voltage, whatever that is going to get divided across these 2 points as 2:1 ratio. So obviously V1 is going to be bigger and V2 is going to be smaller. So V1 greater than V2 is our preferable answer, which means this one is bad, this one is also bad. এটা হচ্ছে একটা স্টেপ। সেকেন্ড স্টেপে আমাদের যেটা খেয়াল করতে হবে সেটা হচ্ছে current is going to come in here and get split into 2 parts. Actually, let me use red. Current is going to come in here and get split into 2 parts, one through here, one through here. And eventually those currents are going to join over here. So the same current that comes in through here is going to flow through this pathway, and then the current is going to get split into these 2 paths once again and flowing through the 2 ohm resistor. Now try to understand. These 2 resistors are exactly equal, which means the current will be divided equally. So this branch will have 50% of the whole current. This branch will also have 50% of the whole current. But if you have a look over here, this resistance is big and this resistance is small. So between these 2 branch currents, which is supposed to be bigger? Which branch should have higher current between these?
Sir, the branch with 3 ohms.
The branch with 3 ohm, because that's a smaller resistance. So even if you don't bother to calculate this, I can simply write the current through this branch, through this pathway, should be bigger than 50%, and the current flowing through this branch should be less than 50%. Now if you compare I1 and I2, I2 is exactly 50% and I1 is bigger than 50%. So between I1 and I2, which one should be large?
I1.
I1. So ultimately we are getting this as our correct response. বুঝা গেছে কি, মানে রেশিওর কনসেপ্টটা বুঝা গেছে কিনা? আর যদি এভাবে করতে কমফোর্টেবল না হয় বা ভুলে যাওয়া কমপ্লিকেটেড মনে হয়, then you can definitely give a value. Let's say choose any number over here and analyze the entire circuit by basic calculation, get all the numbers out. It is going to be a bit time consuming, but you have peace of mind that now I could solve this thing properly and I know that I will get score the mark. Find out all of these numbers and then simply compare those numerical values to get your answer. এরপর কোনটা ছিল? এই পেজে আর প্রবলেম ছিল না, আই এম শিওর। I asked you to start my question number 23. 23 is very interesting.
18 দিয়েছিলেন স্যার,
18 পারছো?
শেষ করতে পারিনি স্যার।
আচ্ছা 18টা তাহলে একটু পড়ো, পড়ে দেখো।
টেন্সাইল স্ট্রেংথ বাড়লে তো টেন্সাইল স্ট্রেইন বাড়লে তো লেন্থ বাড়তেছে
প্রিসাইজলি
বাট ক্রস সেকশন এরিয়া কি সবসময় ডিক্রিজ করতে হবে?
ওই যে বলে দিছে তো ভলিউম কনস্ট্যান্ট বলছে না আচ্ছা ভলিউম কনস্ট্যান্ট বলে নাই বাট ইউ হ্যাভ টু assume that the volume will remain constant because there is no reason the volume of the wire should be increased by tensile strain. So if we pull this setup specimen lengthwise on two opposite sides, the wire is going to become longer and also slightly thinner. In your elasticity chapter, for the sake of simplicity, this getting thinner part was discarded altogether. We only worked our way through the increase of length. But that's not true. For a realistic scenario, for a more realistic scenario, when a wire undergoes elongation, the length increases and also the cross section area also decreases. So both of these factors will attribute towards resistance increase. Right, because R proportional to L, increase of length will give you resistance increase, and R proportional to 1 by A, decrease of cross section area still gives you resistance increase. So both of them will attribute towards an increase of overall increase of the resistance. So in this case, I guess B is the correct response. No, sorry, D is the correct response.
Yes, sir.
বুঝছো সবাই?
জি স্যার।
আচ্ছা 23টা একটু আলাপ করি 23টা খুবই সিম্পল একটা কোশ্চেন বাট স্টুডেন্টরা এই ফিগারটা দেখে গড়বড় হয়ে যায় দেখে এটা বুঝে না বাট ইন মাই অপিনিয়ন ইটস ভেরি সিম্পল কোশ্চেন হ্যাভ এ লুক 23 স্কুলের পরীক্ষা খুব কমনলি আসে তোমরা যখন মক টক দিবা স্কুলে বা কোয়ালিফিকেশন এক্সাম দিবা এটা এক্সপেক্ট দিস এমসিকিউ টু শো আপ an electrical power cable consists of 6 copper wires C surrounding a steel core এই কথাটাকে ভালো করে বুঝো this is a cable it means it's a long wire that's cross section area looks like this which means the wire actually looks like this this is the cross sectional view of the wire let me take it over here I'm going to skew it a little bit to make the diagram understandable and then I'm going to draw that wire black so this is how the cable looks like within this cable you have a steel core going through lengthwise and which is surrounded by 6 copper wire I mean why this construction like this is not none of your business but just because I want to tell you that steel practically gives the strength of the cable so that it can hold up its load so that you can hang the wire with large gap between the poles so that you have less pole to use for the whole transmission line the steel is there for the more of the strength part and copper is over there for the higher conductivity part so that you have less loss and you have less heating in the wire and you can transfer more electrical energy to the consumers the question tells us that now you have to understand if we have current flowing through here how would the current flow current is going to essentially flow through all of the 6 cores side by side this is very much similar to that question that we had come across a bit earlier for a setup like this very much similar like this here you have to assume that there is one steel wire among these 7 and 6 of them are copper wires all of which are currently in parallel because they're going to carry electricity simultaneously side by side parallel combination so if you understand the concept of parallel combination rest of the problem is pretty simple because the question has already told us that 1 kilometer of the copper wire has a resistance of 10 ohm and 1 kilometer of the steel core has a resistance of 100 ohm so what is the combined resistance of 1 kilometer length of a power cable so what will be the combined resistance that's pretty simple if I just go ahead I'm going to write 100 inverse 1 plus 10 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 inverse 1 1 2 3 4 5 plus 10 inverse 1 whole inverse that's basically a combined resistance the reason I wrote so many 10 inverse 1 but not 6 into 10 inverse 1 because I didn't want to confuse you if I did write like this this would be a much shorter form of writing but you might be confused that where did this 6 multiply come from that just not to confuse but you can write this in your calculator if you understand the significance that if you understand these two are exactly the same but if you don't get this properly or if you're confused go ahead and write the whole thing no big deal take a little bit of time but be sure about your output বুঝা গেছে কি
Yes, sir.
এখানকার বাকি কোশ্চেনগুলো অ্যাকচুয়ালি খুব আচ্ছা এটা তো অন্য পেজে চলে আসছে we're at here এখানকার বাকি কোশ্চেনগুলো মোটামুটি সহজ, খুব বেশি ঝামেলার কিছু এখানে দেখতেছি না। এখানে মনে হয় আর কিছু দেই নাই, দিছি এটা কি দিছিলাম 29
No, sir, 29.
22 দিয়েছিলেন স্যার, ওটা বোধহয় রিপিট।
কোনটা?
22
22 is 22 easily পারবা। আচ্ছা 22 দেওয়ার কারণটা কি সেটা আমি বলি, মানে ইটস এ সিম্পল কোশ্চেন বাট why did I give 22? একটা জিনিস খেয়াল করো, এখানে বলছে হচ্ছে two wires P and Q are made of the same material or the same length and are connected in parallel to the same voltage supply. So we have two wires connected to the same voltage supply, which means the V is same for both of them. This is P and Q, where P has a diameter of 2 millimeter, Q has a diameter of 1 millimeter. Understand that these are diameters, these are not cross-sectional area. What you should know that area is given by pi r square, or if I can write pi into d by 2 whole square, which can give me pi by 4 d square, which tells us that the cross-sectional area is proportional to the resistance squared, or cross-sectional area can be also proportional to diameter squared. And we know that r is proportional to 1 upon a. So if we combine these, we can also write that r is proportional to 1 upon r square, or r is proportional to 1 upon radius squared, diameter squared. So this relationship can be very helpful for us. Why is this important for you to understand clearly? Because whenever you try to figure out their resistance variation, because they have different diameters, you cannot directly take this ratio. You have to take the square of this ratio. So let me show you. I'm going to show you this math in a very simple mathematical way, which I personally find to be fascinating to go for. It makes good sense. Although this is a pretty simple problem, there's not much magic in it, but still, have a look. The question says, what is the ratio between the current in P and current in Q? So we're trying to calculate IP by IQ, which should be given by V divided by RP by V divided by RQ. V and V crosses out, and if we flip, we get RQ divided by RP. Now resistance equals to what? Rho. Both of them have the same material, so rho is same for both of them. And then what is this? L, the same length, so L is also same for both of them. So L over here remains the same. Now Q has a diameter of 1 millimeter, so we can write pi into 1 squared. You want to wonder, sir, how about the millimeter? I'm not bothering about the millimeter because I'm just trying to find out the ratio. I know that the millimeter square will cross out. So pi divided by 1 square, and over here pi divided by 2 squared. So get rid of the similar stuffs in both sides. So you get 1 by 1 divided by 1 by 4. So you basically get 4:1. So this is the correct response. বুঝা গেছে কি? এইভাবে করলে যে সময় সুবিধাটা হয় সেটা হচ্ছে ভুল হওয়ার প্রবাবিলিটি কম থাকে। বাট তুমি যদি বেসিক রেশিও ইউজ করে যদি মানে মেন্টালি ক্যালকুলেট করে ফেলতে পারো ইফেক্টিভলি উইদাউট এরর, দেন ইউ ক্যান অলসো ডু দ্যাট, নো প্রবলেম। আমি এই মেথডটা দেখালাম মানে লিখে করার সুবিধার জন্য। বুঝা গেছে কি ভবান?
Yes, sir.
আচ্ছা, we are out of time. I will pick up 10.3 and 10.4 inshallah next class. I want you guys to attend this problems. আমাদের next class হচ্ছে টিউসডেতে। টিউসডেতে না?
Thursday, sir.
Thursday তে।
আচ্ছা থার্সডেতে হলে তাহলে আমি আরেকটা এক্সট্রা ক্লাস প্ল্যান করতে যাচ্ছি। আজকে তো হচ্ছে কি বার? সানডে। আমরা কি টিউসডেতে একটা এক্সট্রা ক্লাস নিতে পারি সকালে সেম টাইম?
সকালে কখন স্যার?
সেম টাইম 9টা থেকে 11টা। আমি এত আর্লি দিচ্ছি হচ্ছে মোস্ট লাইকলি তোমাদের অন্য কোচিং গুলি থাকে না, সো ইফ ইউ ডোন্ট হ্যাভ স্কুল ক্লাসেস মেবি ইটস পসিবল ফর ইউ টু।
স্যার উজমার না স্কুল থাকে, এজন্য আজকেও আসতে পারে নাই, ও আমাকে বলছিল কালকে।
আচ্ছা উজমা স্কুল কটা পর্যন্ত?
এটা ওর 10টা থেকে শুরু হয়, 10টা থেকে বোধহয় 12টা বা 11টা পর্যন্ত, আবার 1টা থেকে শুরু হয় আরেকটা ক্লাস বা এরকম কিছু বলছিল।
তাহলে কি আমরা 8টা থেকে নিব?
নিতে পারেন স্যার, অসুবিধা নাই।
No, these are extra classes just to make up for the lost gap. I mean, this will not be a perennial thing. This will not be a continued thing. I just want you to get to the bottom of this thing. And now I have time. I'm a bit more stable than before. And also I can actually wake up before 8. Which is miraculous for
Okay,
me,
sir.
but it's true. Acha, let's schedule a rough plan for an additional class on Tuesday 8 a.m. to 10 a.m. And I'm gonna post this thing on the group chat. And if some of us have really hard time to get to this, we might actually discuss a different time frame. Irrespective, the lectures will be uploaded in the YouTube. So if anyone have to, or if you cannot do the classes at any point, you can always take feedback from there. No big deal. For the timing, goodbye. Allah
Yes,
Hafiz.
sir. Assalamu alaikum, sir.
Wa alaikum assalam.